Have you ever wondered why atoms, the tiniest building blocks of matter, don't just collapse into themselves if electrons are constantly circling a positive nucleus? That was the mystery troubling scientists after Rutherford's model. According to classical physics, an electron moving in a circular orbit should emit energy continuously. And if it loses energy, logically, it should spiral inward and crash into the nucleus. But clearly, matter around us is stable, atoms don't implode. More importantly, when we examine light emitted by hydrogen, we don't get a smear of colors. Instead, we get distinct lines, a line spectrum. Rutherford's model, while revolutionary, simply couldn't explain these specific frequencies. Why do atoms release only selected wavelengths of light? Why is the atomic world so selective and stable? These puzzling observations led scientists to seek a model that could explain atomic stability and the discrete nature of atomic spectra. That journey led to Niels Bohr.
Bohr entered the scene with bold new ideas. He proposed that electrons don't randomly orbit the nucleus, but are restricted to specific, allowed circular paths called energy levels or shells. Here's the game changer. While revolving in these permitted orbits, electrons do not radiate any energy. They stay put, maintaining their energy, like a train moving on a fixed track without losing fuel. Now, what happens when an electron shifts between these tracks? That's when energy is either absorbed or emitted. The energy difference between the two levels determines the frequency of light involved. Mathematically, it's expressed as E2 minus E1 equals h multiplied by nu, where h is Planck's constant and nu is the frequency of emitted radiation. Even more fascinating, Bohr stated that the angular momentum of an electron is quantized. In simple terms, the product of mass, velocity, and radius of the orbit must equal n times h divided by 2 pi, written as m times v times r equals nh by 2 pi, where n is a whole number. Let's explore this idea of angular momentum further. It's not just any momentum, it's circular momentum. Bohr suggested that an electron's angular momentum is fixed in quantum-sized chunks. Imagine trying to spin a basketball only at fixed speeds. No slow-mo, no in-betweens. That's what Bohr suggested for electrons. The expression mvr equals nh by 2 pi defines it clearly, where m is the electron's mass, v its velocity, r is the radius of its orbit, n is a positive integer, and h is Planck's constant. This equation told us that electrons can't just orbit at any random distance. Only those where this condition is satisfied are allowed. This discrete nature prevents the electron from continuously radiating energy, a key reason atoms remain stable. It also beautifully matched the experimental data from hydrogen's spectral lines. Suddenly, atomic behavior wasn't random. It was rule-bound, predictable, and quantized. Now that we know electrons can occupy only specific orbits, can we actually calculate how far they are from the nucleus and how much energy they carry? Absolutely. Bohr gave us the equations. For hydrogen-like atoms, the radius of the nth orbit is given by r sub n equals 0.529 multiplied by n squared divided by z angstroms, where z is the atomic number. So, for hydrogen with z equals 1 and n equals 1, the radius is 0.529 angstroms. That's the Bohr radius. As for energy, it's given by E sub n equals minus 13.6 multiplied by z squared divided by n squared electron volts. That minus sign indicates that the energy is bound. The electron is locked in by the nucleus. As n increases, the energy becomes less negative, meaning the electron is less tightly held. This is why outer electrons are more easily removed. These equations let us quantify the very structure of the atom, something unimaginable before Bohr. Here's where Bohr's model dazzled the scientific world, explaining the mysterious hydrogen spectrum. Each bright line in hydrogen's spectrum corresponds to an electron jumping from a higher to a lower energy level. The frequency of light emitted is given by h multiplied by nu equals E2 minus E1. For instance, when an electron falls from the third orbit to the second, it emits visible light, part of what's called the Balmer series. Transitions to the first orbit give rise to the ultraviolet Lyman series, and transitions to the third produce the infrared Paschen series. Each series is like a musical note, played when electrons fall between particular energy levels. As you can see in the energy level diagram on screen, each drop creates a unique spectral fingerprint. Bohr's model matched the observed lines precisely, a triumph that turned theory into trusted explanation. Let's now apply Bohr's formulas to solve a quick problem. Say we want to calculate the radius and energy of the second orbit in a hydrogen atom. We're given n equals 2 and z equals 1. Using the radius formula, r sub n equals 0.529 multiplied by n squared divided by z angstroms. We get 0.529 into 4, which equals 2.116 angstroms. For energy, we use E sub n equals minus 13.6 multiplied by z squared divided by n squared electron volts. That's minus 13.6 divided by 4, which equals minus 3.4 electron volts. So, in the second orbit, the electron is about 2.1 angstroms from the nucleus and holds an energy of minus 3.4 electron volts. This clarity in numbers makes Bohr's model not just a theory, but a practical tool to compute real atomic values. So to wrap it all up, Bohr's model took us leaps ahead in understanding atomic structure. It introduced the radical idea of quantized orbits, solved the mystery of line spectra in hydrogen, and provided equations to calculate energy and radius with amazing accuracy. However, science keeps evolving. Bohr's model worked well for hydrogen, but couldn't explain the spectra of more complex atoms with multiple electrons. It also couldn't handle phenomena like the Zeeman effect, where spectral lines split under magnetic fields, or account for the wave nature of electrons. Despite these limits, Bohr's contribution remains foundational. He built the bridge from classical mechanics to quantum theory. I hope now you see how this model was a turning point, turning the atom from a mystery into a marvel. See you in the next class, where we'll explore even deeper into the quantum nature of atoms and beyond.